Imagine you could hand a padlock to a complete stranger in public, in broad daylight, with 100 other strangers watching the whole exchange happen. Anyone could pick it up, lock a box with it, and hand it back to you. But here's the impossible part. Nobody who touches that padlock, not even the person who used it, not even everyone watching combined, can ever open it again. Only you can. How does a lock like that even exist? That's not a hypothetical. That's happening right now. Every single time you open a website with a small padlock icon in the address bar. Every password you type in, every bank transfer, every private message, every card number, all of it depends on a stranger being able to lock something for you without ever being able to unlock it themselves. Most people think encryption works like a diary with a key. Lock it, unlock it, same key. Done. That's the assumption almost everyone makes. It's also completely wrong. The actual mechanism behind almost all internet security doesn't use one key at all. It uses two. And the reason that works is stranger than fiction. Here's the myth. People assume secure means secret, like whispering a password nobody else can hear. But modern encryption isn't about whispering. It's about math that only runs one direction. Think about mixing paint. Mix yellow and blue, you get green. Easy. Now try looking at that green paint and separating it back into the exact yellow and exact blue you started with. You can't. Not because it's hidden, because the process only works forward, never backward. That one-way trick is the entire foundation of internet security. It's called a trapdoor function, and it's the reason two total strangers who've never met, being watched by every hacker on the network, can still agree on a secret code in plain sight. Here's how it actually plays out. Say you and a website both agree publicly, out loud, on one starting color. Yellow. Everyone watching knows it's yellow, including anyone trying to eavesdrop. Now, privately, behind closed doors, you pick your own secret color and mix it into that yellow. Nobody sees your secret color, only the muddy result you get afterward. The website does the exact same thing, on its own, with its own secret color nobody else knows. Now comes the swap, still fully in public. You hand over your mixed result, the website hands over its mixed result. Anyone watching the network sees both of those muddy colors travel across the wire in plain sight. Here's the move that makes it work. You take the website's mixed color and add your secret color into it a second time. The website takes your mixed color and adds its own secret color into it a second time. Something strange happens. Even though neither of you ever saw the other's secret color and neither of you ever sent your secret color anywhere, you both land on the exact same final color. An attacker who watched every single color cross the network, the starting yellow, both muddy mixtures, everything, still cannot work backward to extract either of your original secret colors. Mixing forward takes one step. Unmixing takes something closer to guessing every possible combination that could have produced it. That's the trapdoor. Easy to walk into, brutally hard to walk back out of. That handshake is real. It's called a key exchange, and your device runs a numerical version of it every single time you visit a secure site, before a single word of your data gets sent anywhere. Here's the part almost nobody realizes. That entire color mixing process, the trapdoor math, is actually too slow to protect your whole conversation with a website. It's brilliant, but it's heavy. So it only gets used once for a few milliseconds to do exactly one job. Agree on a single shared secret. The moment both sides land on that same final color, they immediately switch over to a completely different, much faster type of encryption to protect the actual data, using that freshly agreed secret as the one shared key. That faster system is closer to the diary lock most people originally imagined. Same key locks and unlocks, except now the key itself was born out of a handshake nobody watching could ever reverse engineer. Slow, unbreakable math to agree on a secret. Fast, simple math to actually use it. That combination is what makes browsing feel instant while staying secure. Once that shared secret exists, this is where the two-key system comes in properly. A website publishes what's called a public key. It's exactly like that padlock you handed to a stranger. Anyone can use it to lock a message, but unlocking it requires a completely different key, the private key, and that one never leaves the website's server. It's never transmitted, never exposed, never shared with anyone. So when your browser locks your data using that public key, it genuinely does not matter if a hacker is sitting right there watching the entire exchange happen in real time. They can grab the locked box, they can even hold the exact same public key you used to lock it. It changes absolutely nothing. Without the private key, that locked box is just noise. Here's a second myth worth killing while we're at it. Encrypted does not mean invisible. The box itself, the size of it, when it was sent, who sent it, and who received it, none of that is hidden by this process. Only what's written inside the box gets locked. An observer watching your connection can't read your messages, but they can often still tell that you connected to a certain server, roughly how much data moved and roughly when. Encryption locks content. It was never designed to hide the fact that a conversation happened at all. Now here's the part that actually breaks most people's assumption of what secure even means. Encrypted doesn't mean unbreakable. It means unbreakable within a useful time frame. The math behind these locks relies on problems that computers are catastrophically slow at solving in reverse, like factoring an enormous number back into its two original prime components. A modern computer could technically try every possible combination. It would just take longer than the age of the universe to actually get there. Security here isn't a wall nobody can climb. It's a wall so impossibly tall that by the time anyone finishes climbing it, whatever was behind it has stopped mattering entirely. That's also exactly why encryption keeps getting upgraded every few years. Quietly, in the background, without you ever being asked. It's not because the old locks got picked. It's because computers keep getting faster, and a wall that used to take 1 billion years to climb might eventually take 100 or 10 or 1. So the math evolves, the keys get longer, and the trapdoor gets deeper, permanently staying one step ahead of whatever's trying to reverse it, long before anyone actually catches up. There's one more piece worth understanding, because it explains why this whole system can be trusted at scale. When you connect to a website, your browser doesn't just trust any public key handed to it. It checks that key against a certificate, something like a digital notarized signature, issued by an organization your device already trusts. That's what stops someone from just handing you their own padlock and pretending to be your bank. The lock has to come with proof of who actually made it, or your browser refuses the connection outright and throws up a warning instead. There's also a genuine threat on the horizon, and it's worth naming honestly. Quantum computers don't just run faster, they solve certain math problems in a completely different way. And factoring those enormous prime numbers happens to be exactly the kind of problem they're built for. A sufficiently powerful quantum computer could, in theory, climb that impossibly tall wall almost instantly. That's not science fiction panic. It's why researchers are already building and rolling out entirely new trapdoor functions, ones that stay hard even for a quantum computer to reverse. The wall gets rebuilt before the old one is ever actually scaled. So next time you see that small padlock icon sitting quietly in your browser bar, this is actually what's happening behind it. Your device and a server, total strangers who will likely never interact again, agreed on a secret in full public view, using a lock anyone could pick up but only one side could ever open. Not because anything was hidden from view, not because anyone whispered, because the math only runs in one direction, and running it backward costs more time than anyone watching actually has. That's not a metaphor for privacy. That's the literal mechanism keeping nearly everything you do online private, running quietly every single time in under a second without you ever noticing it happened at all. That's not a metaphor for privacy. That's the literal mechanism keeping nearly everything you do online private, running quietly every single time in under a second without you ever noticing it happened at all. If that padlock trick messed with your head a little, wait until you see what happens the instant millions of people try to hit the exact same server at once. That's next. We're breaking down load balancing, the actual mechanism deciding which server picks up your request the moment you hit send, and why getting that decision wrong for even a second can take an entire platform down. If this finally made encryption click for you, genuinely helps this channel grow. And if you want more mechanisms broken down like this, subscribe so you don't miss the next one.